Good morning all. Today we are going to see finite word length effects in digital filters, and also we will see fixed point and floating point number representation. Now in finite word length effects, what do you mean by actually finite word length effects? When digital systems are implemented either in hardware or in software, the filter coefficients are stored in binary register, right? So these register can accommodate only a finite number of bits, and hence the filter coefficients have to be truncated or round off. That is, the process of quantization introduces an error in the signal which is called the round off noise, right? So there are various kinds of error. One is input quantization error, product quantization error, and coefficient quantization error, right? Next, so before that we will see how to quantize the numbers by seeing the review of number system. It actually in number system the quantities are expressed in numeric symbols, right? So it generally it is expressed in integer as well as in the fractional part, right? So generally an analog and digital system can be represented. An analog system can be represented as the physical quantities or signal may vary continuously over a specified range, right? So the digital systems can be expressed as the physical quantities or signals that can assume only discrete values. Now we'll see how to represent. Now we can represent this by using, there are various types of number representation. There are three types of number representation. Actually these are used to represent the numbers in digital computer or any other digital hardware. One is fixed point representation, another one is floating point representation, and next one is block floating point representation. Now we are going to see fixed point representation and floating point representation. In fixed point representation, the position of the binary point is fixed. So the bit to the right represents a fractional part and the bit to the left represents the integer part. Okay, right? So the fixed point in fixed point representation, bits allotted for integer part and fractional part are fixed. So the position of binary point is also fixed, right? So and at the same time the negative numbers can be expressed in sign magnitude form, 1's complement form and 2's complement form. It's clear, right? Now in sign magnitude form, the most significant digit is set to 1 to represent the negative sign. For example, I am representing minus 1.75, which is represented as, right? So this red color one, it represents the negative number, and for 0.75 the binary is actually 1100, and for 1 it is actually 001. So I am representing here as 1, and this red one represents actually minus. Similarly, for positive 1.75 is represented as, for positive it is a 0, right? And 1.1100 and so on, right? Next, actually this sign magnitude numbers, to represent negative integers we need a notation of for negative values, right? So actually the conversion is to make the sign bit 0 for positive and 1 for negative, right? So for example, if I see the sign magnitude representation of a particular number is say 1 0 0 0 1 0 0 1, then in 1's complement I can represent actually inverse of that number, and in 2's complement is actually 1's complement plus 1 of that number, right? And next we can go for an signed binary numbers by doing arithmetic subtraction. Also we can use the 2's complement. This and all you might have studied earlier, right? So now I am going to represent addition of two fixed point numbers. For example, I am taking 0.5 and 0.125, right? So first what I am going to do is I am going to add these two numbers. Obviously I am going to get it as a 0.625, but before that I am going to convert a decimal into binary. Similarly 0.125 decimal into binary. Okay, so we are going to assume the total number of bits is number of bits plus 1, which is equal to 4, including the sign bit. So when two numbers of b bits are added and the sum cannot be represented by b bits, an overflow is said to occur. Always there will be a overflow will be there, right? So for example, actually 0.5 and 0.625, when I am representing in terms of any number, that is in terms of this sign overflow, actually here it is minus 0.125. Clear, right? So the overflow occurs in above result because 1.125 cannot be represented in 3-bit number system, right? Addition of fixed point number causes an overflow, right? So the subtraction of two fixed point numbers can be performed easily by using 2's complement representation, right? Similarly, we can do the multiplication of fixed point arithmetic, right? Take example of 2 bits, right? So these 2 bits you multiply, right? So if b bits are organized into b equal to bi plus bj, then the product may contain 2ba plus 2bj bits. Okay, so in fixed point arithmetic, multiplication of two fraction results in a fraction. For multiplication with fraction, a overflow can never occur actually, right? Next, we will go to the floating point representation. In floating point representation, a positive number is expressed as f equal to 2 exponent c dot m, where m represents mantissa and c represents the exponent part, right? So here is an example for 32-bit single precision floating point number, right? So this actually s represents sign, it's a sign bit, and this is an exponent, right? And then it is going to be the fraction, right? That is a mantissa part. Clear? Now, so negative floating point numbers are generally represented by considering the mantissa as a fixed point number. The sign of the floating point number is obtained from the first bit of actually mantissa, right? So I can that is do an arithmetic multiplication also in the floating point representation. So what we can do is we can get that is the product of two mantissa m1 and m2, and similarly exponent is actually c1 plus c2. Okay, to correct the problem of exponent, we can have a c1 plus c2. It should be altered, right? See, I had given some of the examples, right? 1.5 which is in decimal, you just convert in terms of that is binary, right? And the binary equivalent also I had given here, right? So to carry out addition, first adjust the exponent of the smaller number until it matches the exponent of the larger number. Then the mantissa are then added and subtracted. So we can do the addition of and the subtraction of two floating point numbers, but are more difficult than the addition and subtraction of a fixed point numbers. And next, suppose we are adding 3.0 and 0.125. Okay, right? So 3 can be represented as actually a 0 1 1, right? So 0 1 1, and now here I am going to represent in mantissa and exponent form as actually here it is 2 0 1 0, because we are just moving the decimal point only towards 2 values. So it is 0.11000, and for 0.125 there is no actually there is no integer part, so we are representing with 2 power 00 into 0.001000, right? Now so we adjust the exponent of smaller number first, so that both exponents are equal. Now I am adjusting the exponent of smaller number. After adjusting that, I can go for adding or multiplication of two numbers, right? Now first let me talk about the fixed point arithmetic and floating point arithmetic differences. Actually in fixed point arithmetic there is a fast operation, right? And here in floating point there is a slow operation. Actually in the fixed point, if you see, there is a overflow of occur during the addition. but actually here there will not be any overflow arises during the addition. Okay, so and then fixed point representation can be used only in small computers, and it is used in large computers, like your floating point represents in large computers. Next, so after representing all the that is number representation, let me start with the quantization. Now, actually, quantization is nothing but a quantization or quantizer. So, a discrete time continuous amplitude signal into a digital form, right? So, while doing the quantization for most of the application, the input signal is continuous in time or in the analog waveform. So, what I have to do is I need to convert into digital by using A to D converter, analog to digital converter, right? So we need a sampler circuit, right? And then we need to have a quantization. So the signal x of t is sampled at a regular interval of time t is equal to nt as per sampling theorem and Nyquist criterion, right? So these numeric equivalent of each sample x of n is expressed by finite number of bits giving the sequence xq of n. That is nothing but actually the quantization error. The error actually introduced in representing the continuous valued signal by a finite set of discrete level is called quantization error or quantization noise. Or I can say simply it is the difference between quantized value and actual sample value, right? So there are two methods of quantization. Actually we have seen in the introduction itself. There is a truncation and rounding, right? So first we need to truncate, then we have to go for the rounding. Now your truncation is nothing but the process of discarding all bits less significant than least significant bit that is retained. Okay, so that is called actually truncation. Suppose if we want to truncate the following binary numbers from 8 bits to 4 bits, right? For example, I have a 0011, right? 0011, 0011, then I can truncate it to only 4 bits. When we truncate a number, right? So the signal value is approximated by the highest quantization level that is not greater than the signal. It is clear, right? Next. Rounding. Actually, rounding is the process of reduce the size of binary number to finite word size. Rounding is the process of reducing the size of a binary number to finite word size. Okay, right? So 0.11010 is rounded to 3 bits is either 0.110 or 0.111. Okay, right? That is actually rounding. So rounding up or down will have a negligible effect on accuracy of computation in general, right? So here actually after this we will calculate the quantization of noise, right? So this is what your quantization mechanism. First let me round off, then we'll have a truncate, then we will go for the magnitude of truncation, right? So I already told you that what is quantization noise, right? So quantization noise is actually it is nothing but it is the difference between quantized value and actual sample value. It's clear? Or we can say the error introduced in representing the continuous valued signal by a finite set of discrete level is called the quantization error or quantization of noise. Thank you.